Hello, today we're going to be talking about discrete random variables. So what's a discrete random variable? Well, a variable is a characteristic number or quantity that can be measured or counted. A variable can also be called a data item. Age, sex, business income, expenses, country of birth, class grades, eye color, and vehicle types are all examples of variables. There are two major categories of variables. There are discrete variables and there are continuous variables. There are a few subcategories, but we're going to focus on these main two. So when a discrete random variable is something that is countable, and a continuous random variable is something that is measurable. So something that's countable, if I were looking at the number of siblings each person in class had, well, the number of siblings is countable. It's not something I measure, it's something I count. And if I were looking at the height of all of the students in class, that is something I would measure. It is not something I would count. Furthermore, to illustrate this point, if I were to draw on a number line and I wanted to represent discrete, countable numbers, well, it would look like this. I'd have points. And in this case, I have points at all the integers. If I were to draw what a continuous random variable would look like, or the possible outcomes, then I would need to draw in a line. So something that's countable is only going to contain the whole numbers here, and something that's measurable contains all of the points in between 0 and 1, all of the points between 1 and 2, between 2 and 3, and so on. It can take on, and actually these can take on an infinite number of values. So let's take a look at a few different examples. So the amount of gasoline in your car's tank. You need to ask yourself, do I measure that or do I count that? Well, I don't know about you, but I measure the amount of gas in my car's tank. I don't know of any way to count it. So this would be continuous. Ratings for a movie. And if we're thinking about the number of stars a movie gets, do we count that or do we measure that? Well, the number of stars are something that we would count, so those count, so those are discrete. Distance a football is thrown, do we measure it or count it? We measure it, so this is continuous, because the distance can take on an infinite number of values. Value of the tips received by a server. Do we count tips or do we measure them? We count them, so this would be discrete. Okay, so in class, we actually created a probability distribution when we counted the number of words we got correct in the correct order. So all of the possible outcomes, getting 0 correct or all the way up to getting 10 correct, that's called a sample space. That's all the possible outcomes that can happen in an event. In order for something to be a probability distribution, two things have to be true. The first thing is that the sum of all my probabilities has to be equal to 1. So if I want to write that in English, I'm going to write this out in English, and you'll see why we like math symbols better. The sum of all of the probabilities in a sample space must equal 1. Okay. So you can see this is a lot shorter to write. The second condition that's true is that each individual probability has to be greater than or equal to 0, but less than or equal to 1. So let's write that out in English. Each individual outcome must be greater than or equal to 0, but this is greater than or equal to 0, less than or equal to 1. Okay, and that makes sense because you can have a probability of 0%, but you can't have anything less than 0%. And the probability of something happening could be 100%, but it's never going to be greater than 100%, and it can be any value in between those two numbers. Okay, so here I have an example. The following data represents the number of games played in each World Series from 1923 to 2013. Create a probability distribution. So from 1923 to 2013, that's a difference of 90 years. And if I add all my frequencies together here in the second column, those do total up to 90. So that's the total number of years. And then over here in this first column is the number of games that were played that it took to win the World Series. And again, that second column is how many times each of those years occurred. In the third column, we're going to calculate the probability of winning the World Series, the number of games in the first column. So if I go and I want to know the probability of winning the World Series in 4 games, I'm going to use past data to calculate the probability. It happened 18 out of the last 90 years, or that 90-year span. And when I turn that into a decimal, I get 0.2. The rule for decimals is that you need to keep one more decimal place than you started with. Since I have a frequency of 18, that's a whole number. I want to round to one more decimal place. All right, and then the probability of winning the World Series in 5 games. Well, number of games played is 5 here, happened 18 times, and then the total is 90 games played in the last 90 years. And that is also 0.2. All right, and when I get to 6, winning it in 6 games, that happened 20 out of the last 90 years. And when I round this, or when I turn it into a decimal, I get 0.22. So I'm going to round that to 0.2. And then the last one is 34 out of 90. And I actually get 0.38, but I'm going to round that to 0.4 because that rounds up. And now I can check to see if this is a probability distribution. So if I look at each individual probability in this last column, 0.2, 0.2, 0.2, and 0.4 are all greater than or equal to 0, but less than or equal to 1. So one of my conditions is met. The other condition is that all of these probabilities have to add up to 1. So when I check that, 0.2 plus 0.2 plus 0.2 plus 0.4 does indeed add up to 1. So this is a probability distribution. So I'm going to take that same data and let's calculate the probability of the World Series lasting only 4 games. So only 4 games. 4 is only 4. 5 is more than 4, not only 4. So we're really looking for the probability of 4. And that is 0.2. I just go to my table over here. Probability of 4 is 0.2. We've already calculated it. Once we get to this stage, it's pretty easy. All right, next question. What's the probability of the World Series lasting at least 5 games? I always have, so these kind of play mind tricks on me, the at least, at most questions. So this is the key here, is to be careful. And then I always talk myself through it. So I say, is 4 at least 5? No. 5 is at least 5. Is 6 at least 5? Yes. And then that means 7 is as well. So what I'm looking for here is the probability of 5 plus the probability of 6 plus the probability of 7. And that's going to be 0.2 plus 0.2 plus 0.4. And I'm getting these values over here from the table. The probability of 5 is 0.2, the probability of 6 is 0.2, and the probability of 7 is 0.4, which gives me a total of 0.8. What's the probability of the World Series lasting no more than 6 games? So again, I have no more here. And I ask myself, is 4 no more than 6? Yes. Is 5 no more than 6? Yes. Is 6 no more than 6? Yes. Is 7 no more than 6? No. Let's fill in our probabilities. They're the same as they were before. I don't know what happened to the table. So we're looking for here the probability of 4, and the probability of 5, and the probability of 6, which is going to be 0.2 plus 0.2 plus 0.2, right? I want the probability of 4, and the probability of 5, and the probability of 6. 7 is more than 6, and we want no more than 6, so we do not include that. So I get 0.6. Okay, I have a second example. This table shows the probability for the number of items that a shopper can purchase. First thing we want to ask ourselves, is this a probability distribution? Again, we're going to look at this last column over here and see, are these all values that are between 0 and 1, 0 and 1 included? So the probability of purchasing no items is actually 0.2. The probability of purchasing 1 item is 0.04, and the probability of purchasing 2 items is 0.1, and the probability, I think this is a mistake. This number here should be 0.4. That's a typo. All right, and then the probability of purchasing 3 items is 0.3. So if I want to know if this is a probability distribution, I look at all these values. That 0.2, 0.4, 0.1, and 0.3 are all greater than or equal to 0, but less than or equal to 1. And then I check my second condition. Passes the first condition. 0.2 plus 0.4 plus 0.1 plus 0.3 all adds up to 1. So that makes this a probability distribution. All right, again, I need to correct this data entry. All right, we're going to calculate the following probabilities. What is the probability that a shopper purchased 0 or 1 item? So since we already have the probabilities calculated for us, we can look here at 0. That's 0.2 or 1 is going to be 0.4. So the probability of 0 or 1 is 0.6. The probability of purchasing more than 2 items. So again, you got to be careful and ask yourself, 1 is not more than 2. Is 2 more than 2? No. 2 is 2, but it's not more than 2. So we're not even going to look at 2. But 3 is more than 2. So really what we're asking is for the probability of 2, or 3, sorry. And that's just 0.3. These are only tricky because of the wording. So I recommend strongly that you talk yourself through it. So the probability of at least one item. Is 0 at least one item? No. Is 1 at least one item? Yes. Is 2? Yes. Is 3? Yes. So here we're looking for the probability of 1 plus the probability of 2 plus the probability of purchasing 3 items. And when I add those up, I'm getting the values from the table above. The probability of 1 is 0.4. The probability of 2 is 0.1, and the probability of 3 is 0.3. Adding those up, I get 0.8. Hopefully you've gotten a calculator by now so that you don't need to do this by hand, but we can also calculate the average number of items a shopper bought. We can calculate the variance and the standard deviation. If you don't have a calculator, you're going to have to learn to do this by hand. So I'll go through an example with you. But these are the formulas. They should already be written on your sheet. Let's go through, though, before I go through this example. This symbol here is the mean. So it's equal to, this is the sum of my value, that's the x value, times the probability of that value. And then the variance, this is the symbol for variance. That's the population symbol. If I were talking about sample variance, that's s squared. This should have a square next to it. So in your notes, looks like there's a typo on your notes. This should have a square with it. That's the symbol for variance. Sum of the mean, the value minus the mean squared times the probability of x, each individual value. And then to find the standard deviation, you just take the square root of all of that. Really, I strongly urge you to get a calculator because this will be so much easier and quicker. All right, so if you don't have a calculator, here we have the number of items in the first column. In the second column, we have the probability for each number of items. And so I broke down the formulas into simpler pieces. So in the first column, we have the value, the data value, number of items times the probability of buying that item. So the value in this is x over here, this is the probability of x. So 0 times 0.2 is going to be 0. Oh, I love when that happens. 1 times 0.4, I'll do this, is 0.4. I really like that too. 2 times 0.15 is going to be 0.3. And 3 times 0.25 is going to be 0.75. So those are all the individual values times the probability of that value. So I need to calculate the mean before I can calculate that third column, because if I don't, I won't have the mean to put in there. So the mean is going to be the sum of x times the probability of x. So we're going to take all of these values from this column here, and we're going to add them up. So we have 0 plus 0.4 plus 0.3 plus 0.75, and that means that my mean is going to be 1.45. That's what I get when I add all of these decimals up together. Okay, so that's the average number of items that shoppers bought. All right, so let's calculate this fourth column here, so that we can get a standard deviation and a variance. So 0 is the x value, and we subtract the mean, which is 1.45. That's going to be negative 1.45, and when we square it, we get 2.10. So we started out with one decimal. We're going to add one more. So 1 minus 1.45 squared is going to be 0.2025. We'll just leave it at 0.20. And then 2 minus 1.45 squared is going to be 0.30. And 3 minus 1.45 squared is 2.4. All right, and then in my last column here, I'm going to take this value from this column and multiply it by the probability, which is this column here. So I have 2.1 times 0.2, right? Probability, let me change colors here. This column is this, and this is this column. I'm going to multiply those two things together. And over here, I get 0.40 in this column I get 0.08 . And this column I get 0.05, and then the last column it gives me 0.6. So for the variance, I'm going to add all of those up. I'm going to add up this last column here. That's for variance. So I get 1.45. And then standard deviation, I just take the square root of that. And I end up with 1.06. Okay, so again, I recommend you get a calculator if not for eliminating a lot of stupid errors that you might make trying to calculate all that, but for speed too. That's it for tonight. We'll practice this in class.